Yeah, okay. Now we will be moving to the theories in the gaseous breakdown. So as I said, in this lecture we'll be dealing with the theories. Okay. So the first theory is called the Thomson theory. Okay. So it's very important. If you're studying this Thomson theory and this Paschen law itself, you can surely attend your 13 marks from your what you can say. So you need to you can write it out. Okay. So the second thing is your streamer theory. Okay, first thing is your Thomson theory. Second thing is your streamer theory, and the second part we'll be seeing about the Paschen's law. Okay. So the PPTs may be somewhat in a disordered manner, but I have covered based upon the concepts. I have arranged based upon the concepts. I'll say what are the concepts. Okay. We'll be moving into mechanism of breakdown. Okay. So in general, what happens is that there are two types of breakdown in gas. Okay. So in your tau formation in the previous unit, we have seen about the charge separation theory. Okay. So after the charge separation theory, these two are the next theories which are responsible for your breakdown mechanism in a gaseous state. Okay. So here the two things are Townsend theory followed by streamer theory. So the main difference between these two theories lies in the electric field. Okay. Lies in the electric field. So that is, for Townsend theory, you will be having a uniform electric field. Okay. In Townsend theory, you will be having a uniform electric field, whereas in streamer theory, you will be having a non-uniform electric field. Okay. So this arrow has to be coming down this way, this fashion. Okay. So that's the main difference. So you already know about uniform electric field and non-uniform electric field. You might have studied in the second year with respect to electromagnetic theory. Okay, that is, if there is a point charge, okay, just remember it. If there is a point charge, if it is subjected to electric field, okay. So I'll be going with the paint. So, for example, I take this thing, okay, and take this a point charge, okay. This is your point charge. Okay. If this point charge, see, if this point charge is subjected to an electric field, okay, it is subjected to an electric field of intensity E. Okay. It is subjected to an electric field intensity E means, and the E doesn't change. Okay. Here, electric field E, field intensity E is constant throughout this crossing of the point charge means, then you can say your point charge is subjected to a uniform electric field. Okay. Okay. So that is, it will be coming with the respect to vector quantity. So E vector. The same concept you can take it out. You can take it out the same concept. You can take it out. That is a single point charge P, which is subjected to an electric field, but this electric field is not uniform. That is, the point charge will be subjected to electric field E1 at this surface. Okay, that is, before the point charge P will be subjected to the electric field intensity E1, and after the point charge P, it will be subjected to an electric field E2. So what happens is that one half of the point charge will be experiencing the electric field E1. The other half of the point charge will be experiencing E2. So this corresponds to your non-uniform electric field. Okay, so this is non-uniform. Okay. So your point charge is subjected to non-uniform electric field, and this will be your uniform electric field. Okay. So in this, throughout the point charge, the electric field will be E only, but over here, one half will be having E1 and other half will be having E2. Okay. This is what you have to understand with respect to your electric field. Okay. So now moving on. Moving on. Based upon this, only they have been classified your theory. So if it is acting in a uniform electric field, then the theory which you have to follow is Townsend theory. So for a non-uniform electric field, you have to go with your streamer theory. Okay. So from Townsend theory, you can expect many kind of questions. Okay. So we'll be moving on. The Townsend theory, one of the main important principle is this thing. Nothing but your electron attachment process. Okay. This electron attachment process is similar to the concept what we have seen in your previous lecture. Okay, the concept is the same. Okay. So now, we have to see what they will be saying. Okay. So what they are saying about this concept is the types of collision in which electrons may be attached to the atom or molecule to form a negative ions are called attachment collision. Okay. So this thing is similar to your what you can say covalent bond formation in your what you have studied in your chemistry. So in your chemistry, you might have learned about ionic bond formation followed by your covalent bond formation. Okay. So this electron attachment process is similar to that of your covalent bond process. Okay. So what they are saying is the negative ions like when you come to this equation, you will be understanding. Okay. The saying is that take out a stable atom. Okay. The stable atom is subjected to some negative ion. Okay. Subjected to some electron. Okay. So what happens is that after this, so here K refers to the energy. Okay. K refers to the energy. So what happens is that this atom becomes a negative atomic ion. Okay. Negative atomic ion. Okay. So the gases in which the electron attachment plays an important role is called electronegative gases. So this is possibly in your highly electronegative gases. So again, you have to go to your chemistry. So in your periodic table, you can see your electronegative gases are separately grouped under your halogen element. Okay. So highly electronegative element, you can take it as fluorine. I think fluorine is a highly electronegative thing. So with respect to that, we'll be studying. This is a normal basic equation. Okay, they are asking electron attachment process means you have to write the process and followed by this equation. Yeah, I said right. Fluorine. So fluorine is your high electronegative gas. So with respect to your fluorine, this refers to sulfur fluoride, that is SF6. So which you have already studied. They'll be using this SF6 in your circuit breakers. In your circuit breakers, they'll be using this SF6. Okay. So this why they will be using this due to the high electronegativity property of this fluorine. Okay. So what it does? It gives high breakdown strength to the gas. Okay. It is used to remove the free electrons from the ionized gas when arc interruption occurs. Okay. This concept we have already seen in your PhD. So what are the other highly electronegative gases means? These are the examples. Okay. So the breakdown with respect to your electronegative gas is also of two types. Okay. So one is by direct attachment and another one is by dissociative method. So in the previous slide, we have seen a single atom will be bombarded by your electron, okay, to form separate ions. So it comes under dissociative attachment. So this is an atom, so it will be bombarded with an electron, and finally these ions will be separated. So that's what they have given. So for a direct attachment, what happens is that this atom won't be separated. It will be the same, but this electron will be one of those of this A or B. So if it is attaching with respect to this A or B, what happens is this atom becomes a ion. Okay. That's what here they will be saying. Okay. So this is the equation what we have to see through. Okay. So here is the okay. So this Townsend criteria will theory will be mainly based upon this electronegative gases. Okay. So this you have to see is not this equation. So the main equation what you have to see is this thing. Townsend breakdown criteria for attaching gases. Okay. So here this is the criteria. Okay, I'll be explaining in the derivation about this each and every parameter. So separately in 2 marks they might be asking this criteria condition also. Okay. So next is time lag for breakdown. Okay. So in order to breakdown to occur, okay, in order for the breakdown to occur, there may be some kind of lag in the lag, okay, before or after the breakdown. Okay. So what they are saying about this lag is that you can take it as two types. One is statistical time lag and another one is formative time lag. Okay. So these are two types of time lag. So just wait a minute, I'll be back.
Hello, sir. சார் இருக்கீங்களா சார்? ஹலோ சார், இருக்கீங்களா சார்?
So, yeah, so what you can say is for a breakdown to occur, so there will be some kind of time lag. Okay. So other thing is it is defined as the time difference between application of a voltage sufficient to cause breakdown. Okay. That is, at a particular point, the charges start to build up. Okay. From that time period to the time period where your dielectric strength gets broken. Okay. So that's the time period for the lag of the breakdown. Okay. So it is of two types. One is statistical time lag and another one is formative time lag. So what PS they are saying is time in which the lags between the application of voltage which is sufficient to cause the breakdown. Okay. And the appearance of initiating electron. So what I have said is the same thing they are specifying. That is, it is the time period wherein the particular point where the charges start to develop. Okay. So next, this formative time lag is nothing but the time is required for ionization process to develop fully or cause the breakdown of the gas. Okay. So in that formative time lag only the breakdown occurs. Okay. So your total time period T will be equal to the summation of these two time lags. So next we'll be getting into the Paschen's law. So this is one of the important law. We just see through the what is the Paschen's law. So while taking the Townsend's derivation, I will be dealing with it. So these alpha and sigma are nothing but coefficients. Okay, coefficients. So I'll be dealing with the Townsend criteria. At the time I'll be saying about this. So the what is Paschen law? You have to know. Okay. So they're saying in order to account for the effect of temperature. Okay. So here comes the effect of temperature that is given by your gas law. So this gas law I already studied in your chemistry. PV equal to nRT. Okay. So what you're saying is your Paschen's law is the thing what gives the voltage. Okay, it gives the voltage which is needed for the breakdown. Okay, so Paschen law defines the voltage which is needed for the initiation of your breakdown. So this is a function of, so F into N refers to function. Okay, here N is the density of the gas molecules. Okay. So this is the basic equation here too. 24.22 plus 6.08 by root D into K V per centimeter. Okay. So this one will be coming under the derivation part. Okay. So I will be posting the derivation part also after a few lectures I will be posting. Okay. The next is a limitation of your Townsend's theory. Okay. So it is based upon the current growth process. Okay. Generally what happens, the current growth will be happening by your ionization process. But in practical condition, it doesn't alone not depends upon the ionization process. It also depends upon your gas pressure and the geometry of the gas. So this in turn depends upon your Paschen's law. So your Paschen's law is saying about this concept only. Okay. So next is the time lag. So in general, your time lag will be of order 10 power minus 5 seconds, but here in practical conditions it will be 10 power minus 8 seconds. Okay. So next is the discharge. The discharge, what they're saying, it predicts a very diffuse form of discharge. Here, your in practical condition, the discharge will be irregular. It will be irregular. Okay. So next they have given about the application. Okay. Just see through it. So next we'll be moving to the non-uniform field. So I have told about your uniform and non-uniform field with respect to your points as I have already said. Okay. So now what is the thing is that we'll be getting into the non-uniform field. So in the non-uniform field, the electricity intensity will not be the same. It will be of each of the one will be of different magnitude. Okay. So now we'll be getting to the streamer theory. So your streamer theory, what it says? In general, your streamer theory is about the electric field discharging in your non-uniform field. Okay. So your streamer theory takes place in the non-uniform field, whereas your counterpart Townsend will be taking place in a uniform. Okay. So what here it is saying is, so who had proposed this theory was Racer, Meek and Lowe. What they said was predict the development of spark discharge, okay, directly from a single avalanche. Okay. So this is what you have to know. So similar to your avalanche breakdown in your electronic devices, this streamer theory occurs in the real time. Okay. So here with the spark discharge, this is from a spark, there will be a possibility of some avalanche formation. Okay. That is like train formation. It keep on forming, in which the space charge developed by the avalanche itself is said to transform the avalanche into a plasma streamer. Okay. You are seeing the diagram means you will understand. So this is streamer theory. You will be taking out with the anode and a cathode, and you will be applying the electric field, that is a very high voltage electric field, to create this air particles. So what happens here is, so there will be a space charge. Okay. So if I am getting into the space charge concept, means it will be taking a very long time for me to explain. Okay, you just Google it, what is a space charge. Okay. So what happens is, it is in general you just have like this space charge is nothing but a cumulative of charge. Yeah. So from a particular point, this rise to an avalanche. Okay, so this will be your spark. Okay. So next diagram of the image will be early understanding. So this spark will be able to tend to rise the other uh, stream. So this refers to a stream. Okay. So it will be like a stream-like structure. How it is happening means through the increase in your base charge, you can say. Okay. So this charges gets increasing. So first it initially started from a single point. From a single point it started out, and now it gets multiplied. Okay, multiplied in the form of a string. Okay, so finally you'll be getting in this fashion. Okay, so this is possible only in your non-uniform electric field. Okay, why in the sense means that each point the electric field intensity will be different. So the space transformation will lead to the particular path for the stream. Okay. So if the space charge formation in some part is the higher need, so the stream will be moving towards that path. Okay. Like that fashion. Okay. So that's with respect to your streamer theory. So here, other thing is electric field estimation. How they will be estimating is they'll be using this formula. Okay. You just have a idea about these formulas alone. Okay. Again, they will be going to the breakdown in non-uniform field. Okay. This alpha is called as the previous slide we have seen about the alpha and the gamma. So those are nothing but your Thomson ionization coefficient. Okay, I'll be taking that. Okay, when I'm taking that, I'll explain about it. Okay. So here in unit, we have seen about the Thomson criteria for breakdown in uniform field. We have seen. So here, for your non-uniform field, this is your criteria. Okay. So this is the same equations I have seen. Okay. So from this, a possible question what they'll be asking is they'll be asking through the mechanism of the breakdown in uniform field, followed by the, so in mechanism of breakdown in uniform field means it refers to your Townsend's theory, followed by mechanism of breakdown in your non-uniform field means it refers to your streamer theory. Okay, so after that they will be asking what is the Pascal's law in 2 marks, and they might be asking to explain about the electron attachment process. So that's also will be coming under 2 marks. Okay, so that's all with respect to today's lecture.